Viitorul e al tău, noi punem temelia. Construim pentru România. Universitatea de Construcții București.
Thank you, Loretta, for the kind invitation. I'm very pleased to be here again in Bucharest. It is a very familiar place for me. And today's event comes back to a conversation we had 2 years ago, and we managed to bring it into reality. This is the first step, and we believe that we will enforce and will continue, and the collaboration of the two societies will strengthen even more. So let's begin with a presentation. It is more static now, again back, and also it is always a difficult part. After 3 very interesting lectures and distinguished lecturers, and before lunch. So I hope I will keep a little bit of your interest. Up, down. So, what's all about the second generation of Eurocode is for structural and geotechnical engineering. I have found this figure somewhere from ASCE. I do not know the exact source. I tried to, but I'm not sure where it is. So, but it is a very nice figure that portrays the need for geotechnical investigation. And we will begin with the soil properties and the partial factors of safety, the first 2 components. We will go back to the basics, because one of the most important things in this sequence of the geotechnical design is the estimation of the soil properties, and most importantly the geotechnical investigation and the interpretation of this. So the new Eurocode introduces some new terms, and we need first to understand them and then to get the appropriate interpretation. And this is also important so that we can communicate with the structural engineers. And all right. So we have these 4 definitions. We have the characteristic strength, which is more or less what Loretta said. It is the 95 probability of the mean or the inferior value based on a hypothetical unlimited test series. This is a statistical method. And we have the nominal strength, which is a new term, which is the well-known cautious estimate of the same mean or inferior superior value based on previous experience and on similar conditions. And this is the empirical method. Both can be used to take the representative strength, either independently or in having both information. And we may also apply a conversion factor for scale effects, moisture, temperature effects, material aging effects, and generally any other parameter that will affect the material property throughout the project's lifetime. And if we use a material factor approach that we talked about, then we also need the yes, here it is. Then we need the partial factor of safety for the material factor approach on the strength. To put this in a sequence of how we determine the strength, we begin with a characteristic strength. It can be from statistical analysis, which gives the representative value, or in parallel by the nominal value, which is selected by knowledge of the construction site and experience in comparable cases. There are 2 types of characteristic values. The first type is the characteristic value of the mean, while the second one is the inferior 5% or superior 95% value, the fractile. So we have the mean estimate, which is the best estimate. This can be from statistical methods, back analysis, or empirical methods. And then we have this value here, which is the confidence interval of the mean. or the cautious estimate of the mean value, as we say. This is normally used. And then we have the individual value, which is the prediction interval of the individual value. Here is the 5% fractile of all possible values of the material property. Oh, going back. So, Eurocode 7 adopts a general formula of there's something with the equations here. The general formula of the characteristic value, in which we have the sample mean, a statistical sample value. We have the variation coefficient, again a statistical sample value, the standard deviation over the mean value, and we also have the statistical distribution coefficient for the required confidence level. This depends on various things and also on the type of Vx, or the variation coefficient. These are the three types of the variation coefficient. We have case 1, the known, where the Vx is known from prior knowledge. This might come from evaluation of previous tests in comparable conditions. The comparable means determination by engineering judgment. Case 2 is the assumed, where the engineer uses indicative values. These are included in Eurocode 7 Part 2 for ground parameters and test parameters. And there is case 3, where we determine the soil property. We derive them from ground or test parameters, from the tests that we use from, that we get from the geotechnical investigation. So let's put this again into a line, and to begin with, the statistical characteristics of case 1 and case 3, the known and unknown, are normal distribution, 95% confidence level, and infinite degrees of freedom. While case 2, it is a student's distribution, 95% confidence level, and the degrees of freedom depends on the model. If it is a single parameter model, n-1, or n-2, if it is a twin parameter model, like the Morkulov one. And what we said about the mean value, the type A and type 2, are summarized here in these four equations of Kn. So, for type A, we may have the normal distribution or the student. For type B, again the normal and the student, and the difference is in this factor, which gives a lot lower value of the soil property. Where to use which? Type A and type B choice depend on which value dominates the behavior of this problem or of the system. If we say that we have a slope stability problem, most likely it will be type A. The extremes do not play that much a role. If we have a bearing capacity problem and let's say a single pile, then we may shift towards B, where the extreme values may play an important role. While if you have a pile group, that the overall failure mechanism includes a large volume of the soil, then we may use type A. And so, this is a graph of the Kn value versus the sample size. And roughly we can say that the lower values correspond to the mean, while the upper one corresponds to the individual, the 95 or 5% fractile. And we may say that for a sample size of 10, for practical purposes, the difference is not much important. Well, it is many times that we are happy to have 10 samples, but the important thing is that I want to show you that this procedure may give us an insight on how to choose the representative value. So, For the case 2, where the Vx is assumed, these are part of the indicative values that are being included in Eurocode 7. Undrained strength and, let's say, peak or residual cohesion, there is a great uncertainty on these values, 30 to 50% coefficient of variation. And this is the indicative values for test parameters, SPT, CPT, cone, sleeve. There are also more in the Eurocode. And if we calculate now these values, the coefficient of variation, we need first the mean value and then the standard deviation, the well-known statistical equations. This is the single parameter model in which the application is straightforward. It's what we know, this bell-shaped distribution. We may wish to represent this in a slightly different way, in this way. This is plus minus, okay? It does not recognize this figure. And so it is the mean value, it is, well, the characteristic value is the mean value plus minus a 95% times the standard deviation. And this value, it is either normal distribution or student distribution. This corresponds to the population mean. If we compare this to the inferior value, which corresponds to the individual value, here is the factor n plus 1 squared, times again the probability distribution factors. Now, by knowing this and this, we can also, by knowing the mean value and the standard deviation, we can also apply probabilistic analysis, if we are lucky enough to have the data. Let's go now to the more Coulomb failure criterion example. And let's say the example of the direct shear. In the direct shear, we have, it is a two-parameter model. This is the equation, the well-known. We have the independent parameter, which is the vertical stress, and we have the shear stress. We get data of the independent variable and the measure, which is the response. A regression of this gives the mean value, the black line. And what we want to get is the dashed green line, which is the characteristic one. This characteristic value comes now from a statistical evaluation, again, of the mean or the individual value, in a slightly different way than that of the single parameter model that was shown before, in a slightly different way than this one that we all know. Oh, I'm going back. So, these are the equations. We will not explain them, but the picture is the same. The characteristic value of tan phi k, the mean value, minus A95 times the standard deviation. Again, for the characteristic value of cohesion, the mean value, the A95% and the standard deviation. The A95% can be normal or student distribution. And for the type B, the inferior or superior value, this is the difference, n plus 1 squared. I applied this data, these equations, in a series of data kindly provided by Michalis Bardanis. It is data of granular fill material from a quarry in Etika, Prefecture, Greece. It is the largest direct shear device in Greece and one of the largest in the world, designed by my friend Baldanis, Michalis, and it is operated in Edafos SA laboratory. This is the device, a very specialized one device that applies direct shear to granular fill material. Applying now, we have 23 data points. These 23 data points are practically insensitive of the case. That means of the type of the distribution. That means that we expect that no matter what the Kn value, the type of distribution is, that we will get more or less, for engineering purposes, the same characteristic value for the mean, two cases, and for the individual. So, the first dashed line corresponds to the mean characteristic value of the Morkulov envelope, a CK, which while the solid one, it is the mean value, 50 kPa, 46 kPa. The lower dashed line corresponds to the individual characteristic value of the Morkulov failure criterion, where the cohesion has dropped to 28, 29, depending on the case. There is also a difference in the angle of shearing resistance, 50, 53, 48. If we see here this graph, we see that the first dashed line is a bit lower than the mean. So, if we go and draw by hand what is the expected mean characteristic value of the Morkulov envelope, I definitely believe that we will go lower. This is the tendency, this is our nature to be more conservative. The statistics say something else. And if we go to choose the characteristic value for of the Morkulov envelope for the individual case, then we go very close to the extreme. Now, here I wouldn't expect that. I would like to be a little bit more. Here it covers practically all the data. I would expect to be a little bit higher. But knowing this type of analysis can help us to select the appropriate C and phi value, even if we need to draw it by hand. Most probably we will do it this way. But we need to know what these two values stand for in order to select them appropriately. And this is now the message I want to deliver from this figure. And having determined the characteristic value, we need to get the design value. And there were previous mentions in the consequence class, which according to the EN 1990, we have two different classifications. One comes from two different criteria. The first one is the loss of human life or personal injury. And the second one is the economic, social, or environmental consequences. And it goes from CC0, very low, insignificant, to CC4, extreme and huge. Eurocode 7, part 1, adopts these four, not the CC0, and gives classifications for CC1, CC2, and CC3. This is something new, harmonized with Eurocode 1990. And from this, we get two values of CC. We will choose the most unfavorable one, the higher one. This is an important aspect because this value of CC will give us the consequence factor, as we will see in the next slide. Here are the consequence factors depending on the classification of CC. CC0 is used. So, last week or 10 days ago, I'm not sure, there is a very interesting publication from JRC. Many more details can be found there. I also, this is published in this web page. Currently, type 3, it is 4 guidelines for Eurocode 97. 2 more to come, so I strongly encourage you to visit regularly this web page for the supporting material, for the old one, the existing and the upcoming ones. So let's move now to the ULS partial factors of safety. As mentioned before, we have for the load, for the strength, we have this division of the material factor approach and the resistance factor approach. Well, it is simply putting the factor of safety inside in the property for MFA or outside in the resistance for the RFA. And each one has its own equation. These are not either mixed now as it was before. No gamma R here, no gamma mi here. And concerning the actions, again we have the partial factors of actions, the factors inside, verification cases 1, 2, 3, Loretta talked about them. And we have the partial factors on the effects of actions, VC4, where the factor of safety is outside the equation. So, MFA, RFA, VCs are new definitions for old things, but presented in a more rational way. This is a table that will be part of a table that will be published, we hope in 2025, this year, from Task Group B2, Design Examples. The general equations are simplified, are separate for each factor approach and for each verification case. Here we do not have the gamma E value, or here we do not have the gamma F value. And going into more details, already presented, the MFA case defines the M1 and M2, more or less are the same as before, with this difference of the KM, which is the consequence class factor that already has been described. For M2, each type of strength has its own partial factor of safety, while for the gamma R values, the previous one is in Eurocode 7 part 1. For the gamma R values, the factor of safety, the partial factor outside, this is defined in 7 part 3 for each geotechnical structure separately. Here is a summary that will be presented in this publication. And yes, and no KR has been used for this condition. Consequence classes has not been used for the RFA approach that uses gamma R. Now, let's go to the VC new definitions. For the structural and geotechnical design, we have VC1, already explained. For geotechnical purely design, we have VC3, VC4. What it is about, VC1, we have factors of safety on permanent and mobile loads, VC3 we have partial factors on mobile loads, while in VC4 we have the partial factor of safety outside. In VC1 and VC3, the KF, the consequence factor is applied, not in VC3. To summarize these 4 approaches, here are some colors. So, concerning actions, the VC1 case, the blue one, has characteristic value KF and gamma F, while for the VC3, the KF is not there. Concerning the effects of actions, this is the representative strength of the effects of action times the kappa F and gamma E. So, kappa F still exists for the effects of actions in VC4. Concerning strength now, the MFA is what we presented, the RFA, the factor of safety outside, no kappa R for RFA. To summarize, okay, it is the same picture presented in a different way, but with improved definitions that have a better meaning. This is the correspondence with the first generation, DA1, DA3, DA2, DA2 star. It is all here. Nothing different, but better definitions that also come into better agreement with Eurocode, with the rest parts of the Eurocode that are not geotechnical. Let's see how the consequence factor class affects the factor of safety and the definitions. In all cases, the CC2 or GCC2, it is where the blue and the orange are not applicable. And if we have a big, high importance, high exposure building, then we have CC3. And CC1, it is foundations supporting buildings with low occupancy. While for the geotechnical complexity class, this includes these descriptions. It applies if any one of the following applies, then it is GCC3. Ground uncertainty, considerable, high variable, difficult ground, high ground and surface water sensitivity, high ground structural interaction complexity. For GCC1, all of the following must apply. The opposite of these ones, more or less. Negligible ground uncertainty, uniform ground, low ground and surface water sensitivity, low ground structural interaction complexity. And to put it in a simple example, let's assume that we have a foundation for a public building. This means CC3, which gives these consequence factors. While if you have significant uncertainty of ground conditions, this gives GCC3. Together, these interact in this matrix to give the GC3, which is the geotechnical category, and the Eurocode 7 describes ways to ensure the required reliability and level, also Eurocode 0, Loretta explained about that. So, these classifications correspond to measures to ensure the reliability that we will have the desired results, while this one is for analysis purposes, purely. And if we put all these factors, partial factors of safety together, and we try to get an equivalent total, let's say, factor of safety, gamma for the case A and B, which corresponds to the old DA approach, these are the case. C, it is the old DA3 approach, this is the K, and here are the old DA2 approaches. So, let's move to the bearing capacity. We talked about the characteristic strength, we talked about how we select the partial factor of safety. Now we shift to the ultimate limit state. We have two ways to do this. One is to use the bearing capacity equations, the limit state analysis, which ends up in applying an equation of limit equilibrium condition. For the bearing capacity, we have the undrained conditions and the drained conditions. Let's assume a very simple condition case, vertical central loading. At the beginning, the undrained strength is a function of the undrained resistance, is a function of undrained strength, geometry, and the applied load. While for the drained condition, it is also a function of strength, C, tan phi, but not only tan phi, but various equations of phi. And this makes a little bit complex. It perplexes the condition. For the undrained condition, the equation is almost linear, and MFA and RFA will practically be equivalent. For the drained conditions, this non-linearity, and in other cases, not only bearing capacity, MFA may give different results from RFA. And when selecting the approach, in my opinion, for the national annex, we have to be careful about that. We may get big differences concerning MFA and RFA when the equation that calculates the limit equilibrium condition is non-linear. I think Eurocode 7 says only about the actions, but it is not only the actions, it is also the resistances that we need to take care about the non-linearity. And I will present a comparison of this via this over-design factor, which is the resistance over the action, which should always be greater or equal to 1 to satisfy our design check criteria. And let's take the ratio of this of the ODF of the MFA approach, VC3 plus M2, over the RFA approach, VC4 plus gamma R. And we see it clearly here in the undrained condition, inside the factor of safety, outside the factor of safety. And then I represented this ODF factor by normalizing also the forces, the applied actions, mobile over the permanent loads. The green one are the factor of safety of the verification cases. While for the case of the undrained, we have this equation. Here are the well-known N factors, NC, NQ, and gamma, in which these play a role. While for the MFA approach, the gamma R is outside. So let's have a graph of this over-design factor for MFA over the over-design factor for RFA versus the normalized actions. The ratio is the vertical axis, the horizontal is the action axis. For the undrained case, for this situation, and this each one curve corresponds to a normalized external pressure over the undrained shear strength. And in all cases, VC3 plus M2, that is the MFA, gives the higher capacity. Because this is greater than 1. Here it is always greater. I do not say that which is right or wrong. I'm just saying that we get different results based on our national experience. We have to be careful on what to choose. And if we do the same for the drain conditions, here it is the for zero external load, the picture is a little bit different. The MFA approach gives higher capacity for all cases in which phi is equals 15, well, this is the lower value, and for cases that cohesion is greater than 0. While the red one gives higher capacity, the red one is the RFA approach, VC4 plus gamma R. In this case, in all cases where the phi value is greater than 25 degrees, the RFA gives higher capacity. While there is this intermediate range of phi greater than 20 degrees and this ratio of fractions that also the RFA gives higher capacity. The red ones here. So this is clearly the effect of the non-linearity of the bearing capacity equation. We need to take this into account. And we will finish by some remarks concerning the ultimate limit state by numerical models. The new Eurocode gives provision for numerical analysis, and it gives many alternatives. These are the basic ones here. We will begin with a representative step. We always begin. So we apply the representative load and we calculate the displacement. This is the SLS verification case, the first check. And then we can choose between output factoring and input factoring. What this output factor about is that we make two additional analyses with the design loads to get the pressure, the stresses in the geostructure, so we get the designed actions, and another analysis where we force the soil to fail. This can be done by applying displacements. And here we get the resistance. And this is the ULS verification case, where ED must be lower than RD. The same equation here, but with numerical analysis. And we may have input factoring, where we have the ULS verification imposing design load, but then we have M2. And by saying M2 it is the strength reduction technique. We begin with M gamma M equal to 1, and then we gradually reduce this up to the condition that the complete structure fails. And this is the second check. So it is a matter of choice. This is a very simple example, and we may represent here the SLS representative step by applying the representative load, and we get the displacements. Here is the ULS output factoring step, where we apply representative values and we force, this is the failure mechanism that is being, that we get by applying the displacement. So we need to get the pressure on the foundation from this analysis. And then it is the input factoring step, in which I do not have an analysis here, but I just tabulated how we will perform even if the software does not allow us to do direct strength reduction technique. We begin with a representative value and we gradually reduce by the gamma m factor the values, careful on what feed to insert into the software, and then we make the analysis. So, this is the design check analysis modes through numerical models. This is an outline. First, we have the construction stage, and the construction, well, it may include many construction stages. And we begin with a representative strength, the representative step, sorry. And where we apply representative values. Now, if we want to make a ULS verification step, this is an internal analysis. We have the two choices, either the output factoring or the input factoring. For the output factoring, we said that we need one more analysis, that we need to bring the structure to failure by imposing displacements, for example. For the input factoring, we reduce the soil strength until the complete structure fails. This is an internal step. It is not used in the following analysis. If we want to go to construction stage 2, then we continue from the representative step 1, which provides the SLS verification. We go to this, and then again internally we apply the ultimate limit state, if we wish. We may know that it will not fail, and it is not, we may not want this. And this procedure continues to each construction stage. Also, the new code, the new version, provides many alternatives for the numerical analysis. This is good. It is not too restrictive, but you have to read not only the tables, but also the text in order to realize that. Sometimes we stick on the tables. This, what is performed here, it is in a table. So, the alternatives are these ones. To apply gamma E strength to input factoring, to output factoring, sorry. The first one is the output factoring, is to apply gamma E to strength in order to utilize the distribution capacities. But let's go to input factoring. We may use the partial factor on the results of the loadings, but I think the most interesting part are these two. We can modify stiffness to counteract the stiffness reductions due to gamma F, gamma M. When we reduce C tan phi, it is a little bit strange to keep the same stiffness, elastic stiffness. There is no direct guidance on that, but we can use this in our analysis. And finally, this is also very interesting. We can also apply reduction factors to structural strength. And this will allow us, probably, to get complex failure mechanisms that we want to explore. Let's say, for a deep excavation, to put a partial factor on the anchor strength or the strut, to reduce the strut strength as well. So, to conclude, the second generation has enhanced harmonization with Eurocode 1990, which eases structural and geotechnical engineers' communication. The ease of use is not only a matter of, it's not a matter of reducing the extent of the document. No, it is much longer. What is meant here is that we have achieved harmonization, which is good to communicate, important for communication reasons. So we have clear definitions of nominal, characteristic, representative, and design values. Knowing the statistical definitions and their determination provides a very useful insight for the types and selection of the representative value for the case that we want to draw this line. I mean, it's good to have a knowledge of the statistical procedure. And the new conditions, the new definitions, more or less correspond to the same design approaches. If we realize that, maybe we will become a little bit more relaxed. Seeing the same things in a slightly different way, but the same things, more or less. And I would say that for ultimate limit analysis via limit equilibrium, we have to be careful when we choose MFA and RFA, when the resistance R is a non-linear function of the strength properties. And finally, the second generation of Eurocodes gives now the tool and the freedom, many choices, on the numerical analysis methods that can be used even for ultimate limit state analysis. These are some references. Ioannis Deliakoulas has worked on some part of this presentation. So, thank you very much.
Viitorul e al tău, noi punem temelia.